Today we are continuing our Challenges to Building Resilient Water Systems webinar series. We created this monthly series of interactive webinars to connect water managers with the most recent and relevant research about climate hazards and climate change impacts to regional water systems. Each webinar will include a 20 to 30-minute presentation, followed by Q&A and small group discussions, so that water managers can connect with and learn from each other. Next slide. Today's speaker is Western Water Assessment PI and Professor of Atmospheric Sciences at the University of Utah, Court Strong. His research group studies climate, especially processes involving the atmosphere and cryosphere. They analyze observational data and simulate atmosphere-cryosphere interactions using models run on powerful supercomputers. In today's webinar, Court will present on one key tool that emerged from a 5-year collaboration between university researchers and Salt Lake City Department of Public Utilities. This tool is called the Experimental Winter Precipitation Forecast, which provides a forecast of December through March precipitation in the Western United States. Next slide. Before we get started, I want to share a bit about Western Water Assessment for those of you who haven't worked with us in the past. Western Water Assessment is an applied research program that produces usable science to help address real-world climate problems. We are based at the University of Colorado Boulder, the University of Utah, and the University of Wyoming, and we work in the Intermountain West, specifically Colorado, Utah, and Wyoming. Western Water Assessment is one of several teams in the NOAA Climate Adaptation Partnerships, or CAP network, formerly known as the Regional Integrated Sciences and Assessments, or RISA network. Next slide. Oh, Court, next slide. Thanks. At Western Water Assessment, we are working to build resiliency in water systems and communities in our region while working on many climate-related issues, ranging from water resource management and drought to climate adaptation and resilience to compound hazards. Next slide. Western Water Assessment differs from a traditional research program because our goal is to produce usable science that helps address real-world problems by directly working with communities, resource managers, nonprofits, and other partners to tailor our work to their needs or priorities. This sometimes takes shape as original research, or other times involves research integration, including things like workshops, webinars, online tools and resources, or technical reports like climate summaries and assessments. Other times it involves providing expertise or presenting at a community or partner meeting. Next slide. We can connect across a number of activities listed on the slide, including climate information synthesis and tools, vulnerability and adaptation exploration, connecting with partners, and more. If you are interested in connecting with us, you can email us at wwa@colorado.edu. And last slide. Today's presentation will be recorded and last about 20 to 25 minutes, followed by Q&A and a breakout group session. Please feel free to submit questions via the Q&A window at the bottom of your Zoom screen, as you can see on the slide. We're running the breakout group discussions after the webinar so that you can connect with and learn from each other. Once I assign everyone a breakout room, you will join by clicking on the Join Breakout Room button from the pop-up message that will appear on your screen, as seen on the slide. We will also launch a 2-question poll before the breakout groups to ask about interest in future webinars from us. Lastly, we'll be sure to share a link to the webinar recording with you once it's up on our website. And before I hand it over to Court, please be sure to take our quick survey before you leave today's webinar. It should only take 1 to 2 minutes of your time, and it will help us plan new webinars and communicate with our funders about our program's impact. Benet will leave a link in the chat window now, and I'll send it out again at the end of the presentation. And with that, I'll hand it off to Court. Thanks.
Hey, thanks very much, Ethan. I appreciate the opportunity to come and share this research with you today. It's great to see many familiar names on the Zoom call. So the title is Emerging Forecasting Tools for Seasonal Water Resource Prediction. Got a gorgeous shot of Sundial Peak in the background there from David White to get us thinking about mountain snowpack and predicting it year to year. This is work that was initially supported by Salt Lake City Department of Public Utilities and has been closely synergistic with Western Water Assessment for its duration. So here's a brief outline of what I'll show to you today. So beginning off with a motivation, simply put, water managers need better climate guidance over the Western U.S., and that's especially true in basins that have little predictability related to El Nino, and so that's been a long-standing problem. We did make some headway on that in our collaboration with the utility, and our science discovery was it's better to consider the combined effects of the Pacific and the Atlantic Oceans. So the Pacific would be the familiar El Nino effect. The Atlantic would be an effect that we have highlighted in our recent research, which I'll share with you today. And then the action from that was to develop a stakeholder-driven online forecast tool, which will debut today. And this is hosted on Western Water Assessment. So the motivation: water managers need better climate guidance. So this is a diagram produced by NOAA indicating the typical effects of an El Nino on the upper panel and a La Nina on the lower panel. And under El Nino, the jet stream shifts to the south. You get wetter than average conditions across the southern United States and northern Mexico, leaving warmer, drier conditions to the north. Under La Nina, the jet stream tends to split around a high pressure area located in the Gulf of Alaska, giving wetter conditions to the north and drier conditions to the south. And many of you probably know that's the La Nina is the basis for this year's forecast. So if you look at the Climate Prediction Center, they have above average chances for anomalously high precipitation over the northwest with drier conditions to the south. So very much a La Nina pattern. The challenge with this forecast framework is that it leaves much of the western central U.S. in the white here with equal chances, meaning we could have, there's no strong indication statistically that we'd expect to have above average or below average precipitation. We could just have an average year, or if these regions of wet and dry conditions shifted north or south, we could get something dramatically different. And so key water resource areas such as the Northern California Great Basin and Northern Colorado reside in this region where we have little predictability coming from El Nino. So this was part of the motivation for a research partnership we formed with Salt Lake City Department of Public Utilities. I consider this to be a real flagship example of stakeholder researcher engagement, and our collaboration over the years has been closely aligned with and strengthened by the mission of Western Water Assessment. And a great example of that is the development of this online forecast tool. So we had the scientific finding as part of our collaboration with the utility, but the conversion of that to an online tool that the public can access and use for forecasting purposes was enabled by Western Water Assessment. So I'm very appreciative for that collaboration. So here's the science discovery. This is about a year ago now. We published in the high impact nature partner journal called Climate and Atmospheric Science. This paper, which is open access, so it's available to the public. And the title there is Atlantic Pacific Influence on Western U.S. Hydroclimate and Water Resources. And so the idea here is that it's not just El Nino that's affecting the Western U.S., it's El Nino and effects that are additionally coming from the Atlantic Ocean. And by looking at them together, we can have a more skillful forecast potentially. And so to make this discovery, we used a century of observations, so 100 years of ocean surface temperatures and 100 years of precipitation over the Western U.S. And then we applied a statistical method to them called maximum covariance analysis. So this is a technique for identifying relationships between two data sets. So not just analyzing one at a time, we're analyzing them together, and it finds patterns that explain the largest amount of shared variability between them. Simply put, we could say, how do they move together? So the method of maximum covariance analysis gives you these patterns in order, where the first one is the strongest or most important pattern, and then the second one after that is the second strongest, etc. And what I'm going to do here is I'm going to show you the first two. So the first pattern is essentially the El Niño Southern Oscillation. So the spatial pattern of the ocean surface temperature is shown on the top, and the associated precipitation pattern is shown by the green and brown shading. So when we have above average sea surface temperatures in the central tropical Pacific and below average west of that, that ocean surface temperature pattern is associated with a well-known El Nino result, where we tend to get above average precipitation over the southwestern U.S. and then below average precipitation in the northwest. And then the pattern can reverse. So the same pattern captures both the positive and negative phases of El Nino. So the flip of this would be La Nina, where you would get cooler than average temperatures in the central tropical Pacific, and you'd get wet conditions to the north and dry to the south. So when we use this method, we get these spatial patterns which show us how the pattern is organized in space, and we also get the associated time series which tell us what phase of it we're in. And so we show those down here at the lower right. The blue time series shows us the variation in time of the ocean pattern, and the orange time series is the variation in time of the precipitation pattern. So we can see these move together fairly well with a significant correlation coefficient. When they're positive together, it's an El Nino condition and you get wet south, dry north. When they're negative together, it's a La Nina condition and you get wet north, dry south. So not much new here. This is a well-known, this has been well known for over 100 years. We highlighted it in the paper, and I show it here to emphasize that this method will give us something that we expect as the first mode. And that's an important check on the quality of the information we're getting from the method. What's new here is a look at the second mode. So the second pattern, we refer to it as the Atlantic Quadpole Mode. And the reason we use the term quadpole here is to connect it to oceanography literature. So there's two Canadian oceanographers here, Loader and Wang, in 2015 identified this pattern over the North Atlantic and referred to it as a quadpole mode. And the term quadpole means four lobes with alternating opposite signs. And I'm going to point them out with my mouse here. So to the right of Iceland, you have a negative region. South of Iceland, it's positive, then it becomes negative again. In the central North Pacific, and then in the subtropical North Pacific, it becomes positive. So 1, 2, 3, 4 regions of alternating ocean surface temperature constitutes a quadpole, and we therefore refer to this as the Atlantic Quadpole Mode. And in contrast to the Pacific mode, it has a lot of strong information in the Atlantic. If I go back to the Pacific mode, the first one, you can see there's not much happening in the Atlantic. It's very strong in the Central Pacific. This mode is weaker in the Pacific and has a strong Atlantic signature. And the associated precipitation pattern is important for us because it's a different structure than we see for El Nino. It's wet over more of the western US, and then the dry region is down toward Texas and Mexico. And it's oriented more northwest southeast than the El Nino, which is more north and south. And then similar to the first pattern, we see that the ocean surface temperatures and the precipitation move together in a correlated way. And the utility of this is when we combine it with El Nino. So if we look at the precipitation patterns that are associated with these two ocean modes of variability. Here's in the upper row, the classic El Nino is wet south, dry north. La Nina is wet north, dry south. In the warm Atlantic phase of the quadpole mode, more of the western US is wet, and then under the cold, it's dry. And then what's especially useful is to think how these modes combine. So here we have a 9 panel where the rows represent the phase of El Nino, and the columns represent the phases of the Atlantic. So for example, starting at the top here, this is El Nino under a neutral Atlantic. And then when you move to the right, under a warm Atlantic, we see there's a shift in the line that separates the wet and the dry. As you go from a neutral Atlantic during El Nino into a cold Atlantic, that wet anomaly that we typically see over the southwestern US, it essentially disappears. So that illustrates how strong the effect of the Atlantic can be on western US precipitation for the example where we have El Nino. Go down to the example where we have La Nina. Similarly, under neutral Atlantic in the middle, we have wet north, dry south. But as we switch to a warm Atlantic at the lower right, that region of especially wet conditions shifts south and expands. Conversely, if we go to cold Atlantic, it shifts north and you have less positive precipitation anomaly over the western US. So those are the patterns that we saw in 100 years of observations, just to illustrate how important they are for this region, or for these 3 forecast regions I have highlighted here. The bars indicate the size of the precipitation anomaly for La Nina and El Nino. And under the middle result here, which is neutral AQM, the neutral Atlantic on each has a very small precipitation anomaly. Essentially, El Nino is telling us nothing under a neutral Atlantic. But what happens under a warm Atlantic is you get an increase in precipitation in all those basins. And then under a cool Atlantic, you get a decrease. illustrating how you get that extra potential predictability by considering these Atlantic and Pacific conditions together. Okay, just a brief remark that the one of the key innovations in this study was going beyond the traditional analysis of 100 years of observations. There have been a number of studies that have looked at these types of patterns in 100 years of observations. We added to that uh, a very unusual, very long climate simulation where my colleague Thomas Reichler ran the climate model that his group uses for 10,000 years at fixed 1990 greenhouse gas levels. And so what that does is it gives us not just 100 years to look at, but gives us 10,000 years to look at with the climate system oscillating through its various phases of El Nino and the Atlantic. And we found similar patterns. So there's the El Nino pattern at the top, dry north, wet south, and then the Quadpole Mode showing up here on the bottom with wet conditions over most of the western US. And then when you combine those together, think about how they interact, you get something which looks similar to the observations, but it's a smoother, clearer picture, very much consistent, but easier to pick out the relationship. So again, under neutral Atlantic and El Nino, you're going to have the classic dry north, wet south. La Nina flips that around, wet north, dry south, right? But then what's interesting is as you move to the right on this diagram, you have a shift in the zero line where the wetter region expands under El Nino, going to a warm Atlantic, shrinks south under a cold Atlantic, and then here for the La Nina condition, shifting to the warm Atlantic expands the wet region, shifting to the cold Atlantic expands the dry region. So we were excited about the potential predictability here. The Salt Lake City Department of Public Utilities, of course, saw the value in this as well, but immediately asked the important question, how do we use it, right? Because it's easy to find the El Nino forecast, but it's more difficult to find the state of the Atlantic. And so that was the motivation for us to work with colleagues at Ceres and Western Water Assessment, develop an online tool that stakeholders can use to track both the El Niño Southern Oscillation and the Atlantic Quadpole Mode, and to get a precipitation forecast from that. So what I'll do here is I will switch my share to the online tool that we developed. And I'll mention that as I had it on the slide before I switched, but I'll just mention important that Prasad Thoda was the one who did the huge amount of heavy lifting in terms of developing this online tool in collaboration with Imtiaz Rangwal and Seth Arons. So it's quite an effort. We're delighted to have the tool online now. And so when you land on the tool, you get the title, Experimental Winter Precipitation Forecast, immediately presented at the top with the expected precipitation anomaly based on the Atlantic and Pacific combined effects. This would be valid from December through March, ending in 2025. Color scale here, the green colors are above average precipitation, the brown colors are below average, and the scale there with 100 in the middle would be average. 116, for example, would be 16% above average. And when you access the tool, you can put in a latitude and a longitude that will place a point on the map and give you the associated local percent anomaly. If you'd like to focus on a specific location, we happen to have that on Salt Lake City right now. And if you scroll down, you get a time series indicating the condition of the Pacific, expressed here as the El Nino index. And that's currently neutral, heading toward a weak La Nina as the forecast. And then on the Atlantic side, we see the state of the Atlantic Quadpole Mode, which is currently in its warm phase. And you can scroll down and look at the current sea surface temperature map. We have weak El Nino visible already in the central tropical Pacific. And then there's a structure in the Atlantic that is a slightly positive warm state. So you can see you have negative, positive, negative, and positive, which aligns with the quadpole in its positive polarity. So that's the information on the forecast page. We also have a validation page. So you can come in here and visually inspect the performance of the model. Say, for example, if we select 1950 and click enter, it will show you the observed precipitation anomalies for that winter associated with our forecast. And I will admit that I picked a pretty decent forecast there because I knew 1950 was pretty good. But have a look through all of them. There is varied skill, of course, with any statistical model. And then we also have a documentation page which explains the science. It has a link to the open access article, and then it shows the basic spatial patterns that we see in the ocean and the precipitation and associated with this phenomenon. All right, that's what I have for you. I'm going to leave it there and be happy to answer questions.
I think right now everybody's playing with the web page, so your questions will come in a moment.
Okay. See, there's a hand up. Angus?
Hey there, thanks for the presentation. Super interesting. I'm wondering if you could just comment on when I think about this kind of, it's a retrospective analysis in the sense that you're looking back at conditions and in sort of the context of warming, is there any sort of concern with how to apply these results to sort of current conditions or maybe future conditions? Yeah, I guess I'm just wondering if you could comment on the non-stationarity concerns or not in this type of analysis.
For sure. Yeah, that's a great question. It touches on a number of important points. One is that it is retrospective in the sense that the analysis is based on looking at the period of November through February sea surface temperatures paired with December through March precipitation of each year. And that's where the strength in the relationship is. As we sit here right now, we face two issues. One is the seasonal change in sea surface temperature that we'll see. So this forecast tool right now is based on the currently observed sea surface temperature, and then as it evolves through the winter season, the forecast becomes more skillful and more aligned with the analysis we did in the paper. So that's the first piece of it. And to address that, we eventually want to transfer the tool so that it's looking at, say, a global forecast system forecast of sea surface temperature. That's one part of the answer to your question. The other one is on the non-stationarity on the longer term. So you're absolutely right. And if you look out at 2080, the sea surface conditions are going to be different. El Nino will be different. The Atlantic will be different. And so those aspects, any significant changes in the dynamics of those modes or how they project up onto the atmosphere and precipitation are not reflected here. This is based on what we've seen over the last 100 years.
Thank you very much.
Yeah.
We have a question here from Chris Benson. What is the proposed mechanism to connect Atlantic temperatures with North American precipitation? How do the SSTs impact the atmospheric patterns?
Yeah, another great question. Thanks. So let's go back to my slides here. The mechanism for the Atlantic, and this is something that we still are looking carefully at in observations and also conducting global climate model experiments. The mechanism for the Atlantic to affect the Western US, we think at this point connects through the tropics. So when there's anomalous ocean temperatures in the subtropical Atlantic, it will affect the position of the belt of storminess that traverses South America, which we call the intertropical convergence zone, stretches over into the Western Pacific. We think that it's the shift in that zone that transfers the energy and the signal from the Atlantic to the Pacific. And we have enough evidence from experiments we've conducted to date to give me the confidence to say that here. It's not quite ready to submit for publication though. So it's that I would say is my best guess. Other possibilities would be ocean temperatures in the North Atlantic can affect patterns such as the North Atlantic Oscillation. And it's possible that we have more circumglobal or upstream projecting Rossby wave effects in the extratropical North Atlantic. So it'd be one of those two mechanisms. My thinking on it right now is that it most likely progresses westward through the tropics.
And a question about when we're going to add the 2020 to 2024 data to the validation page. That's something we hope to add at least through 2023 in the next month or so. And then another question. Have you done any analysis that looks at the relationship of sea surface temperatures, ENSO and AQM, and spring precipitation anomalies?
In short, no. So this analysis has been entirely for winter, because that's partly because the majority of the snowpack is delivered in winter, which provides the water resources that we're motivated to study by the project's design. But certainly there are interactions between the ocean and the atmosphere that extend outside of winter, which is a rich area that I would enjoy and probably find quite fruitful to look at. So I appreciate that. The other piece of it too, when you said the relationship between the AQM and the ENSO, or when Seth read the question that way, that reminds me to mention that there is actually zero relationship between the AQM and ENSO. They are, by the design of this method, completely uncorrelated. So there's, what's happening with El Nino tells us nothing statistically about what we'd expect to happen with AQM. They're statistically independent, and that provides an additional convenient. That is an additional convenient aspect of the method.
Daniel Shepard, I see your hand is up.
So this may be in the paper, and if it is, I apologize. But when you were looking at precipitation anomalies, did you focus on the overall volume of snow, or in this case, the severity of the storms, like atmospheric rivers?
This is a good question. So the analysis in the paper was on total precipitation. So we didn't distinguish snow from rain, and we were using the finest temporal resolution we had was monthly. So if there was a within month event, such as an atmospheric river or a very heavy precipitation event, our analysis didn't go down to that level of granularity. It was more of a seasonal total precipitation analysis. And I'll mention anecdotally that the record snowpack that we had a couple of years ago, if you look at the spatial pattern of that, the moisture influx off the Pacific, whether it be an atmospheric river per se or not, clearly had some role in that. And that was a forecast buster for this method as well.
Yeah, anomalies everywhere, but it'd be interesting to look back at some of our records and see how well it correlates. Thank you.
Yep. Thanks for the question.
Another question, Court. Is AQM summarized in one number, an index? Is there a historical record of that number? Is it available real time, daily, or monthly?
Yes. So it's defined as a single number. So when you have a pattern like this or a pattern like this, the method gives you a time series index to represent how that's varying over time. And so that's what we refer to as the AQM index. So if I go back here, this blue line is what would be more familiarly like an El Nino index. And so we have something analogous for the AQM. I'm showing it on the time series here. And if you look at the forecast tool, you scroll down those two time series there, the one on the right is the AQM index. So it has a value for each month. And we're summarizing that as a seasonal mean for the winter on that time series there. It could, in principle, have a daily value as well. It has a spatial pattern, and you could take the daily sea surface temperature, multiply it by that, combine it to produce an index.
Do you do that at the end of the month? Is there like a lag time?
Yes. So currently we're waiting for the monthly sea surface temperature analysis from NOAA. but in principle, it could be done on the daily. And maybe more importantly, it could be done on the sea surface temperature forecast. So we have right now available to us a model projection of sea surface temperature for the entire winter period. And as I mentioned before, the tool right now is based on the observations monthly as they come out. An improvement would be to make the tool based on the daily or weekly averages, and then an even potentially more important improvement is to incorporate complementary information from the forecast sea surface temperature.
Awesome. Thank you.
Yeah.
What are the next steps to get this to operational use, i.e., using the information to improve seasonal stream flow forecasts for water departments?
Yeah, so another, if I go back to the project here, we summarize in our annual report a couple of a couple of the major findings that came out of the project. The one I highlight here is focused on the climate. My hydrology colleagues and Paul Brooks and others in his group discovered an important relationship between the amount of water in the subsurface, which is available as a measurement in January as base flow. So if you make a measurement of base flow, that's an indication of how much water is in the subsurface, and then the precipitation minus evaporation input to the system. What you get for canyon yield depends critically on that base flow. So we combined that base flow forecast, which is available, or base flow observation, which is available in January, with this precipitation outlook, which you could have in October, and made a suggestion on an operational workflow in our collaboration with the utility here, where they could have the precipitation forecast as early as October, check the January base flow, combine that, and have an improved yield prediction. So, and we developed lookup tables and graphs and some tool interfaces to help make that possible. So I think the answer to your question is it's close. The pieces are there. It's a matter of putting them into the sequence and understanding how different users need different pieces of information at different times in their particular workflows.